Our next speaker that I'm happy to introduce is Dr. Rajkumar Singh. Dr. Singh is the Senior Director of the Kalyani Center for Technology and Innovation, Research and Development at Bharat Forge. The Kalyani Center is a world-class applied research institution, and Dr. Singh will be sharing with us this morning, improvements that Bharat Forge has seen in their early applications of laser peening across a wide variety of applications. Dr. Singh, it's a pleasure to have you join us this morning. We're happy to see you, and we look forward to your thoughts.
Okay, I'm thankful to LSP for giving me this opportunity to share some work which has been done on laser shock peening by Bharat Forge. I will just give a very brief introduction about our company. Bharat Forge is an Indian multinational company involved in manufacturing of components for automotive, aerospace, railways, and so many other segments, aerospace also. And our presence is there in India, Germany, US, France, and Sweden. And we are one of the largest forging company in the world. And with this slide, I will show you that we are having facility for closed die forging, open die forging, and we work on steel, superalloys, titanium, aluminum, all type of material. And we also have expertise in additive manufacturing and metal injection molding. And we have in-house capability for all engineering capabilities like modeling, simulation, and testing and validation, additive manufacturing. Our center also has got a lot of facility for material characterization and mechanical testing, and we are approved by most of the top companies like Boeing, Rolls-Royce, and all. Now, from here you can see that our presence is there in aerospace, railway, locomotive, energy, marine, oil and gas, construction, mining, and of course our basic is automotive, where we do more than 50% of the business. Now coming to the subject, so we have got a wide list of our customers across the world, and the US is one of our biggest market, and we supply a lot of beams and forging to US. Now coming to laser shock peening, the audience present here is already aware of the fundamental of laser shock peening. It is a process which creates some wave on the surface and plastically deform the material locally, and there is some vaporization taking place on the plasma of the surface because some coating is given before this treatment. So ultimately, this is a surface enhancement treatment, and there is a plastically deformed cold work volume. And if you see the last stage 3, then you find elastic strains lead to certain creation of residual stresses. So basic strength of the technology is enhancement of the negative residual stresses, compressive residual stresses, I mean, and due to that there are enhancement in certain important properties. Now I will be covering here 3 type of applications which we have tried, although laser shock peening has got a lot of other applications possible, but in our business we have tried 3 applications. So first one is that we have used this technology for enhancement of dye life through this surface treatment. You must be aware that in the forging business, almost 1/3 of the cost is for the forging die. So any enhancement in life not only saves the cost of dyes, but also increases productivity because we get bigger run in the die. So since it is a high cost involved in this, we took this and then the fundamentally the die failures are because of die wear, die fatigue, and die crack. So if material is brittle, then there can be die crack, and otherwise some of the die fail only because of die wear, because they may fail after 2,000, 3,000, 5,000 forgings. So the die we used was DIN 1.2714, which is equivalent to AISI L6. And the properties are given on the screen. That is, it was having a tensile strength of more than 1150 and yield strength of more than 1,000. And chemical composition is also given here. The dies are given hardening treatment and tempering treatment. So hardening at 850 and tempering at 550. The laser shock peening was tried after all this heat treatment. on the material. So the study was done on the sample scale, and then after it was followed by characterization of the treated material and mechanical testing of the treated samples. So here is the macrostructure and ACM macro graph of the treated material. So we see that lathe martensite formation is there in the area where the laser shock peening has been done, and you can say clear-cut macrostructure having martensite. So this difference in the microstructure is giving additional strength to the dies, and there is some grain refinement also taking place because of this treatment. If you say treated and untreated surface, so these are the two basic things: grain refinement and the increase in the compressive residual stresses, which is expected to give better die life. So we have measured the residual stresses of the untreated and treated dies. So LSP treated dies are shown in the red, and you see that there is a wide difference there in the residual stresses. Untreated dies having minus 200 MPa, whereas the treated die has gone up to plus 500 plus actually. So this is one of the remarkable difference which we have seen, and micro hardness also is showing a lot of increase, because when untreated die is in the range of 380, 385, and treated die has gone for 400 plus. So the UTS and YS, this basic mechanical property, we didn't find much difference because of treatment, but there was some difference, the remarkable difference found in the impact toughness actually. So see, the basic properties increase only 5% or 2%, and there is a very marginal increase, but an impact toughness, we found 3% increase. So basic thing is low cycle fatigue, because we have seen in our long experience that the die life is simulated with low cycle fatigue. If the material is having better low cycle fatigue, it always performs better, it gives better die life. So when we have measured the low cycle fatigue of the treated material, we have got 16% improvement in the fatigue strength of LSP treated material. So this is a very, very conclusive finding, and this plus the wear. So we have done the wear test also, and we have found that in the wear test there is a wear is reduced by 1.5 times. So die should perform better, much better, maybe at least 1.5 times higher. The dies have been treated with LSP, and they are yet to be transferred to Bharat Forge. Once they are transferred, we will undertake the actual die trial in the forging press actually. Some other observations also we have seen in the treated and untreated dies. So there is some deformation regime, and but these effects are not very significant. That's why I will be mainly focusing on the most significant effects, like macro hardness. The effect is very significant. I have discussed earlier also, and this will affect the die life. This misorientation is 0.5 degree corresponding to dislocation density. So any effect on dislocation density will also give a positive outcome in the die life. So for this part, our brief conclusions are that there is a 16% improvement in fatigue life, and wear resistance is quite enhanced, that is 2.5 times, and coefficient of friction is also reduced, because that is also important there, because if after treatment dies are quite smooth, then only it will perform better. In the UTS and YS, we heard very slight improvement. Now we come to next topic. We tried this technology on the crankshaft. As you may be knowing that we are one of the biggest manufacturers of crankshaft. We wanted to see how this technology can help us in using the crankshaft for higher load applications, or getting better life. So the crankshaft chemistry is SI1548. We have tried it on this. And next slide shows the, we have done the treatment in the fillet radius and the areas which are critical, and with our long experience, we find that these are areas susceptible to failure. So we have given the scheme of treatment to LSPT, and they did the treatment accordingly. And now here we did the characterization of microstructure, and we found that there is no major change in the microstructure due to LSP treatment. When we have gone to optical microscopy, the phases are same. This is a pearlite ferrite structure, and there is no major change, so no change in microstructure was visible. Now we have measured the in-depth hardness of the material as at various depth actually, and both the graphs are plotted. So red is showing the LSP treated and blue non-treated. So here also you can see that there is no change in hardness observed due to LSP treatment. Surface roughness, we have LSP treatment and non-treated. So there is slightly increased due to LSP treatment in the surface roughness here. And finally, we have done the bending fatigue test for this. So all the values are in the red for LSP treated and green for non-treated. So this is significant that bending fatigue strength has increased by 16% due to LSP treatment. And when we did torsional fatigue, we didn't find any change, significant change, because torsional fatigue is because this treatment is mainly confined to the surface, and bending fatigue depends on the surface characteristic, whereas the torsional fatigue depends on the microstructure of the material as a whole. So we found 16% improvement is the main finding of this. And now we are doing this test in the larger scale, because this was one crankshaft tested. Now some 20 crankshafts are on the transit to LSP technology USA. When the large number comes, we will treat, and we are looking for some saving in the form that either we will eliminate heat treatment and will get the, if we get required improvement in fatigue by LSP, then we can skip heat treatment, or we can use linear chemistry for the same material and do some cost saving, because unless we have commensurate cost saving, it will be difficult for us to adopt the technology on the large scale. Now we have a third application we have taken. This is we have tried it on ballistic armor plate, because we were thinking that in this also, if there is an increase in hardness and increase in the compressive stresses, this can give positive results in the ballistic application. So here also we have done the characterization of microstructure, and phase-wise there is no change because this is martensitic, temper martensitic structure in untreated and treated material both. Now when we have gone into ACM, then we have found some grain refinement near surface area, which we found in the other application also. So there is some grain refinement observed here. And now residual stresses, there is a very significant rise in the negative residual stresses, because untreated is hardly less than -200, but treated has crossed 700. So for ballistic plates shows compressive stresses, and the depth is up to 0.85 millimeter from surface. And so this is the positive thing. And this is the non-treated, untreated comparison so far on the mechanical properties. So UTS, YS, percent elongation, hardness, and impact toughness. So as such, there is not much change in the mechanical properties. There is only very slight improvement observed in UTS, YS, and elongation. Now, one surprising thing is that when we did corrosion test for the LSP treated material, we got very surprising result. We have seen corrosion life improvement by 4 times. So our corrosion expert is looking into the explanation what might have happened, but this is one of the positive thing because ballistic plate is subjected to corrosion as well as the firing actually from the bullets and other things. So here also the ballistic test is yet to be conducted. The plates will be put in the ballistic center and there will be firing on that. And if we find that that penetration is less and damage to the plate is less, we will decide on this that we can use this technology for our heavy duty army trucks, which we are already manufacturing on a large scale in our place. So this is all I wanted to talk. I think I have finished well in time, and thanks to the organizers. Thank you all. I have finished.
Dr. Singh, thank you. Thank you very much. We'll pause here for a moment, see if there's any questions from the audience. Don't see anything coming through. We had something here. So a question, Dr. Singh, is corrosion in ballistic armor a current concern, or is this just an interesting finding in your studies?
No, these findings are very important for us. That's why we are now trying it on the larger scale, because these findings are on the sample level. I already said that when the actual dies come and we put in service, and then we find the improvement actual die, or the same thing with the crankshaft. And we have also got some result on the axle beams. They are very good results, but due to certain limitations, we are not sharing that because of some our IPR issue. But very encouraging results we have got on axle beam also. And now this is a critical stage when we get 20 crankshaft and axle beam treated on the last scale. We'll take final decision to go to set up a LSP unit and try it commercially.
Okay, thank you. Thank you for that. I guess any other questions before we wrap up? Dr. Singh, that was an outstanding and a very interesting presentation. Thank you very much.